So in this question we're given this compound which has a lot of functional groups. Okay, a halo group, an alkene group, a ketone group and a carboxylic acid group. Just familiarise yourself with those before you start. Make sure you know what the functional groups are, because that's going to help you think about what the reactions are. So halo, alkene, ketone, functional group, carboxylic acid. Right, first one it asks for is NaBH4, and you should have learnt that what NaBH4 does is reduces aldehydes and ketones to alcohols, and that's it. It doesn't touch any other groups. So no effect on the chlorine, or on the alkene, or on the carboxylic acid. That's the important one. Even though it's got a carbonyl group in it, it doesn't react with NaBH4. So it's only the ketone group that's going to react, and it's just going to be reduced to an alcohol. So it's very easy. You just draw same structure exactly. Up here, alkenes left the same, chlorines left the same. But when we get to here, we just have single bond OH instead of the ketone group, but the carboxylic acid is left untouched. Okay, so you need to remember that about NaBH4, not just what it does, but what it doesn't do. It doesn't reduce anything else, only aldehydes and ketones. In B, we're asked what happens with excess sodium hydroxide. Excess is a massive clue there. It's saying it probably reacts more than once. So again, we go through each of the functional groups and say, what could that do with sodium hydroxide? So the chlorine, you hopefully remember, can undergo nucleophilic substitution with ions such as OH-. So that's going to be the first reaction. We're going to substitute that. Alkene group, no reaction there. Ketone group, no reaction there. But the carboxylic acid, of course, acid plus hydroxide will form a salt. So we're going to have two reactions, nucleophilic substitution here and salt formation here. So with sodium hydroxide we can then again draw the product. So we've still got the six-membered ring with the alkene intact there, but the chlorine becomes an OH. Make sure you write it that way round. Again, you know that if you write that, you're going to lose marks. You've got to show that the bond connects. You've got to show that the bond connects to the oxygen. So that's the ring there. This bit is the same. The ketone group is left untouched, but the carboxylic acid group has now just become the sodium salt. So we're going to get that. Okay, and the third one is HBr. So again, we'll go through all the groups. Chlorine, no reaction there. Alkene, yes. Okay, HBr, remember, is one of those things which can do electrophilic addition to an alkene group. Ketone, no. Carboxylic acid, no. So it's just the alkene group. Now the issue here, of course, is that when you add HBr to an alkene, it adds across the double bond. So you'll add H to one end and Br to the other end. But of course it could add either way round. When you have an asymmetric alkene as you have there, you could also add the other way round. So in other words, the bromine could either end up on this carbon or on that one. And you have to know which one it's going to be. So this is the Markovnikov thing that you learnt in the first year. So remember that the way electrophilic addition works is that in the mechanism, so if we just draw this actual alkene out, it might help. So we've got that, and then H and H here. That's effectively what this alkene looks like. Remember, in the mechanism, the HBr with its dipole there attracts out the pi bonding electrons, and you get that to form a carbocation intermediate. So this is where the two possible outcomes come into play, because you could either add the hydrogen on here and get the positive charge there, or you could add the hydrogen on here and get the positive charge there. And what you have hopefully learned is that which one happens most depends on the relative stability of these carbocations. So this one is a primary carbocation because the carbon with the positive charge is only attached to one other carbon. This one, on the other hand, is a tertiary carbocation because the carbon with the positive charge is attached to 1, 2, 3 other carbons. Okay, so this one is a primary carbocation, whereas this one is a tertiary one. And what you need to know, you don't have to explain it, but you need to know that the stability increases in the order primary are the least stable, then secondary, tertiary are the most stable. So this is the most stable one, therefore it's the one that's going to be preferentially formed. And therefore that's going to lead to the product, and of course the product is formed simply by the Br- ion that's created in this stage, coming in here and using its lone pair to bond to that carbon there. So that tells you that the bromine is predominantly going to end up on that carbon, the one that's right next to the ring, rather than the one on the end. Okay, so you've got to revise that, make sure you know the Markovnikov story. But of course the outcome of all of that is that we'll still have chlorine there and the 6-membered ring, but instead of the alkene group we'll just have a single bond there, and the bromine will be attached at that end, because that is formed via the more stable carbocation. The rest of the molecule is unaffected, so we've got this and this, and that's your answer, and that's the end.